Hi, I'm Nathan Mcgregor. I'm a fifth-year PhD candidate in the Department of Earth and Planetary Sciences at the University of California, Santa Cruz. I'm jointly advised by Miriam Tellis and Francis Nimmo. The overall theme of my dissertation is the formation and evolution of planetary bodies in our solar system. And the work I've been doing with Francis over the last few years focuses on Venus, specifically what can we learn about the interior of Venus? How has it evolved over time? And how does it operate? Now, Venus and Earth actually are very similar in many ways. Both have similar radius, mass, density, and gravity. And when you look inside both planets, they have a similar structure, with each possessing an iron core, a hot mantle, and a rocky crust. Now, the second layer here, the hot mantle, which is between the core and the crust, is the focus of the research I've been doing on Venus with the ARCS Fellowship. So here we have Venus again. Again, we have that mantle, the core, and the crust. What I've indicated here is the spin axis. So this is the axis about which Venus will rotate. And then the c-axis here is another axis. And the c-axis is a function of how is the mass, or in this case, the rock inside the mantle distributed, and how is it moving around? Okay. So as the mass changes in the mantle, as the rock gets hot or cold or moves around, the c-axis is going to change. Now, the spin axis always stays where it is at all times, but the c-axis wants to be aligned with the spin axis because this is a much more stable configuration. And so what Venus does is it reorients itself in order to bring the c-axis into alignment with the spin axis. And that's what this looks like here, where the entire planet has actually rotated counterclockwise, as you can see here, where the mountains that were here have now been rotated downwards to the equator. Now, when this process occurs, where the entire planet will reorient itself in order to bring the c-axis into alignment with the spin axis, that reorientation is called true polar wander, or TPW. And that's the process that I've been studying on Venus. So here's a useful video of the same kind of process. What you're looking at is a baby bottle filled with some fluid, and it's being spun on the International Space Station. So it's in 0G, just like Venus. And the fluid inside is moving around as it spins. And the spin axis, as I've indicated here, is never changing. The bottle continues to rotate around that spin axis. But in order to bring its c-axis, which again, the c-axis is just how is that fluid distributed and how is it moving, in order to bring that c-axis into alignment with the spin axis, the entire body, or in this case, the bottle, reorients itself. So what we did is we ran some mantle convection models. So mantle convection models just simulate the process by which all this material in the mantle, this hot rock and cold rock, is moving around. And what we wanted to do is we wanted to see if this is possible on Venus based on just models. We developed a model that moves the mantle material around, moves that rock around, similarly how it should happen on Venus. And what we do is we look at how the c-axis changes. But what we see in our models, 1 and model 2 here, is we look at over the entire model runtime on the x-axis, and the c-axis is on the y-axis. We can see that the c-axis is changing over time. And that's because of the mass moving around. So the amount of true polar wander, which is how much does Venus reorient, is quite significant, about 63 to 70 degrees, which means that Venus is undergoing a lot of true polar wander and is very rotationally unstable. The main goal we've had is wanting to provide some measurements for future Venus missions, Da Vinci and Veritas. Both of these missions will be going to Venus in the early 2030s. Da Vinci will look at the atmosphere of Venus to determine whether it ever had an ocean, whereas Veritas is going to look at the surface of Venus as well as the inside of Venus in order to understand its history and inner workings. And Veritas in particular is the one that, if there is a true polar wander signal, would be able to detect that.